Okay, now the mic is unmuted. It should be working now. It's working? Okay, cool. That was dumb. Sorry about that. Cool. All right. Any questions about what we were doing on Monday? We were talking about probability and rewriting probability as sets and talking about things like that. We also had the quiz. Overall, from what I've graded so far, pretty good. Remember, if that a question doesn't make sense on the quiz, ask me about it. Don't just be confused and put a wrong answer. Like, ask me about it. That'll be very beneficial. Cool. Yeah. Any questions about anything, just in general? Today, we're going to finish up section 8.2, hopefully start on 8.5. 8.5 will be the last material for the test. So we will be finishing with 8.5 on Friday. And then again, we have a test on Monday. Again, if you are OAA or testing services, make sure to put in the request for the test so that I can write it and submit it and everything like that. Cool. All right. No questions about anything? All right. Cool. We'll just get back in with our stuff. We were talking about on Monday, the last thing we talked about is that the probability that something happens is the probability that it doesn't happen subtracted from 1, right? So if, say, my odds of going to Taco Bell tonight are maybe 70% chance, the odds of not going are 1 minus that 70%, so 30% chance, right? It has to add up to 100%, right? Something plus its complement is everything, and everything adds up to 100%. So that's the idea we're going with there. And we'll look at some examples. So remember that the complement of something is everything minus that something. So right, when we're talking about complements, we refer to the universal set. And when we're doing probability, the universal set is our sample space, right? So for instance, if I'm talking about a deck of cards, right, one of my subsets of that could be all of the kings. The complement of that would be every card that's not a king. You put those together, you get the entire deck of cards back. So it says, suppose we divide a space into 2 subsets, E and E complement. Remember, this means complement. If they're mutually exclusive, which they should be, right? Their intersection is 0, and their union composes the entire space, then it's the complement. We've talked about that a bit. Furthermore, the probability of the entire sample space is the union of their probabilities, right? Remember, the union of probabilities is they're individually minus an intersection, but because these are disjoint, their intersection is empty. So it'll always add up to 1. So the probability of something happening is 1 minus it won't happen, or conversely, the probability something won't happen is 1 minus the probability it will happen. For example, if the probability is 0.08, this is 8%, that an automobile tire fails in less than 50,000 miles, what's the probability that it doesn't fail? Well, 1 minus 0.08 is 0.92, which is 92%. Pretty straightforward with that. Any questions about that? Cool. And it makes sense intuitively, right? Either something happens or it doesn't, right? The chance that something happens minus the chance that it doesn't happen. Like putting it together, you should get 100%. So a single card is drawn from a standard 52 card deck. Let E be the event that the card is a heart, and then we find the thing, right? So how many hearts are there in a deck? Well, there's 4 suits in the deck. So it is 52 divided by 4, which is 13 hearts. So the odds that I draw a heart, the probability of it being a heart, is 13 in 52, which is 1 in 4. So what's the probability that it's not a heart? So it's just going to be 1 minus the probability that it was a heart, which is 1 minus 1/4, which is 3/4. So 25% chance I'm getting a heart, 75% chance I'm not getting a heart. We cool with that? Cool, cool. If at any point in time you object to anything I say up here, or you're just like a little confused about a step that I made or anything, just please raise your hand and we will address it. Cool. It says here we can use the information below to give the following about a randomly selected person. Let E be the event the person is type O, and F be the event that the person is Rh negative. So that means blood type negative. So this is like Rh negative, 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 and negative. Cool. So the probability that someone is type O, there's this 7% and this 38% here. So 0.07 plus 0.38, that's 0.45. And then the person is negative. That's just adding up all of these negatives here. Get out my calculator, do this real quick. That's what? 7 plus 6 plus 2 plus 1. So that's 0.16 right there. So now we find the probability of those two being the same. So we can either do this from, right, like doing formulas and everything, or we can do it just by looking at this data. Cool. So probability of E union F. So this is the probability that someone is type O and negative, and that's this chunk right here. O negative is 0.07. This would also be the same as probability of E plus probability of F minus the intersection. So probability of E intersect F. And so we just go in here and we would take E intersect F and we'd subtract that out. Same thing. Cool, cool. This would come out to probability of E is 0.45. Probability of F is 0.16. And then their intersection, so where something is both, I did intersection here. This intersection is 0.07. So that is, let me put this on my calculator again. 45 plus 16 minus 7, 0.54. And so what I meant to say here was we were doing the union. I can do this formula here and just pull out the intersection part and subtract it from adding together the probabilities. Or I could go here and I could find, okay, what's the probability of this and what's the probability of that, and just put all those separate things together. But formula-wise, it's just a little easier. I don't have to like sit and add up all the little individual things. Cool. Then what's the probability of E intersect F? That's just this right here. That's 0.07 we got here. Cool. And then the probability of E complement, that's going to be 1 minus the probability of E. And we said the probability of E was 0.45. So that gives us 0.55. Any questions about that? The important thing here is that we're recalling specifically like the formulas here, like the probability of E union F is probability of E plus probability of F minus their intersection. All right. It says here, a single card is drawn from a standard 52 card deck. Let A be the event the card drawn is a heart, and B be the event that the card drawn is a face card. So there's 13 total cards here. And what are the face cards? The face cards are Jack, Queen, and King. So there's going to be a Jack of Hearts, a Queen of Hearts, and a King of Hearts here. And the intersection of A is hearts and B is face cards. Cool. So then all the other face cards are going to be here. That's going to be the total face cards. There's 3 times 4 suits is 12 face cards total. And there's 13 hearts total. So I'll write here 12 face, 13 heart. So if there's 3 here, this 3 plus something should equal 12. So there's going to be 9 over here. And 3 plus 13 should equal 3 plus something should equal 13. So 10. So what I have here is that there are, oh, I have these backwards. 10 and 9. So there's 13 hearts, right? 10 that are not face cards, 3 that are face cards. And then there's 12 face cards. 9 of them are not hearts, 3 of them are hearts. Any questions about that? This is one of those things like where it would be nice to have like a picture of the entire deck of cards, but I remember some of that information, so I can just kind of write it out this way. Right. Probability of A union B, the probability that I draw something that is either a face or a heart. This is probability of A plus probability of B minus their intersection. And this is going to be probability of A. There are 13 in A, so 13 over 52, plus the probability of B. There's 12 in B, 12 face cards. So 12 over 52 minus their intersection, which is 3. There are 3 hearts, which are face cards. So minus 3 over 52. And this equals 22 over 52. And you could find what the percent is for that in your calculator. Cool. Now I want to find the complement of this. So what are the odds that I draw neither a heart nor a face card? This is just going to be 1 minus the probability that I draw a heart or a face card. This is 1 minus 22 over 52, which is, what's that, 20, no, 30, there we go, over 52. Cool. So the odds that I draw a card and it's neither a face card nor a heart card is 30 and 52. There's 30 of those cards in the deck. Now it says, what's the probability of A complement union B? This one's a little interesting, right? We can sit through and we can logic it out from here. So it's going to be everything that is not a heart or is a face card. So if there's 10, 3, and 9 here, that's a total of 22. So out here is going to be this 30. And so now I can like shade in my Venn diagram to figure out the rest of it. So A complement is everything that's not A. Union B, so with the rest of B. So it's just going to be everything that is not a non-face heart, right? And that's what this is saying. It's something that's not a heart or is a face card. And so that's going to be everything but these 10 cards by themselves. So 42 over 52. And again, I found that just from doing, I can shade my Venn diagram, or I can realize what this is saying. Anything that is not a heart or is a face card. So that's putting those two together. Another way I can do this is mathematically, probability of not a heart plus the probability of being a face card minus their intersection. Right. It's a little difficult to find this part too, so it might not be easier to write out like this. But if you are given this information, it might be easier to do that. Cool. All right. Now, what's the probability that something is both a heart and a face card? Well, let's see, there's only 3 of those in here. So that's just 3 on 52. Right? It's everything that's in that overlap right there. And then the probability of A intersect B prime. This is the probability that something is both a heart and not a face card. Cool. So this is, and do I have another marker maybe? So if B prime is everything that's not B, and then I intersect that with A, maybe I'll use red here. This is A. Everything where there's both purple and red here is my set that I'm considering. It's just those 10 cards right there. This is basically saying how many elements are in A and not in B. There's like what's just in A, not in the complement. And it's this chunk right here, not considering the 3 face cards. So the probability that something is a heart and not a face card, that's all of the hearts that are number cards. There's 10 of those. Cool. And commonly when we talk about probability, we talk about the odds of something, right? If someone has some chances, the odds are maybe 100 to 1 or something like that. And so we talk about probability that way in odds, and we can express that mathematically. Specifically, the odds compare the number of favorable outcomes to the number of unfavorable outcomes. Example, if you're rolling a dice, the odds for rolling a 2 are 1 to 5, right? There's 1 way you can get a 2, 5 ways you don't get a 2. So for example, like playing the lottery, the odds of winning the lottery are like 1 to 2 billion or something like that. Maybe not 2 billion, like 1 to a couple hundred million, right? There's 1 way you could win it, a couple 100 million ways you couldn't, or someone else wins the lottery. If the probability of E is the probability of event E, then the odds for E are the probability of E over the probability of E prime, which is 1 minus probability of E, right? Odds against E, so what are the odds that I don't win the Powerball, right? That's the other way around. There's 200 million ways for me to not win it. There's only 1 way for me to win it. So it's very careful to check the language that is being used there. It's asking either what are the odds in your favor or what are the odds against your favor. And so it can look at some examples of computing odds. For example, let E be the event that it will rain with the probability that it won't rain being 0.75. And it says find the odds for and against the rain. For, right, remember that for, that over here, in favor of was you put whatever you want on top. So if I'm looking for, I put probability of E on top and probability of E prime on bottom. That's 0.3 over 0.7. Cool. Or this is the same thing as 3 to 7. That's the notation. You've probably seen this before. Like the odds are 3 to 7. 3 that happens, 7 that doesn't. Against, we just flip it around. That's the probability of it not happening over the probability of it happening. 0.7 over 0.3. That's 7 to 3. There's a 70% chance that it will rain, 3% chance that it won't rain. And we can also rearrange for this. If the odds for E are A to B, then the probability of E is A over A plus B. So for example, with this, the probability was 3 to 7. So the probability of E is 3 over 3 plus 7. 3 over 10 is 0.3. I could also flip it around and do the same thing to get the probability against. So we look at another example specifically. The odds the Chicago Cubs win the league pennant are 200 to 1. Right. What is the probability that they win the pennant? So the odds are greatly in their favor. And it's 200 over 200 plus 1. That's 200 over 201. And what does that come out to? 200 divided by 201 is 99.5%. Yes. Oh, yes. Odds against. So this is the chance they won't win. Or the chance that they win. What is the probability that they do win? 1 minus 99.5 is 0.5%. Maybe I'll say 0.995 instead. So 0.5%. So the odds are against them here. Thank you for pointing that out. I didn't read that. What's the probability they win? It's the opposite of that. So I can compute the probability they won't win and subtract that from 1. That gives me the probability that they will win. Pretty straightforward there. Or I can recognize this as 1 to 200, and then that's 1 over 1 plus 200, and this comes out to 0.5%. So just making sure that your answer matches up with what's said, right? Nolan pointed out that the question actually says against, so 99.5 being that they win doesn't make sense. 0.5 being the percent chance they win does make more sense. Cool. We can also give the following probabilities for an event, or given the probabilities, we can find the odds for and against. So if the probability of something happening is 8 and 9, the odds for are 8 and 9 divided by the odds that it, so odds that it will happen. I'm confusing myself. 1 second. Given the probabilities for event E, find the odds for and against. So if the odds are this, so it's the probability that it will happen over the probability it won't happen for this one. That's 8 and 9 over, if it doesn't happen, that's 1 minus that. 1 minus 8 on 9. Let me write it out here. That's 8 and 9 over 1 minus that is 1 over 9. And this is the same thing as 8 over 9 times 9 over 1, which is 8. So 8 to 1. Okay, there we go. My bad. 8 to 1. And the odds against, I just flip that around. 1 to 8. So this is the same thing as 8 on 1, or 8 to 1. And that makes sense, right? This is saying that out of 9 total possible ways, there's 8 ways of it happening. And that's what this is saying too. 8 ways of it happening, 1 way of it not happening. If I put those together, I get 9. And do the same thing here. This is the same thing as 65 over 100. So the odds would be 65 ways it does happen, 35 ways it doesn't. Right? These add up to give me the bottom right here, 100%. Odds against, I just flip that around, 35 to 65 there. Cool. Odds like this can be a little confusing, but essentially what this is telling you, this should add up to the total possibilities. This should be for, this should be against. Total possibilities for, against. Cool. It says here if there are 4 red marbles and 3 blue marbles, find the probability that the randomly selected marble is red. Right? There's 7 total here. So the probability that a selected marble is red is going to be 4 in 7. And then what's the odds for selecting a red marble? There's 4 ways I can select it, 3 ways I don't select it. Pretty straightforward. Or again, I can go through and do the process of doing the fractions and everything like that. Probability for divided by probability of against. If the odds of an event happening are 8 and 13, what is the probability? So 8 and 13 or 8 to 13, right? And so the probability is, 8 over 8 plus 13. That's 8 over 21. And then put this into my calculator. Clear, 8 divided by 21 is 38.1%. Cool. So again, this is just re-expressing the probability as the amount of ways it will happen versus the amount of ways it won't happen. That's all odds are saying. Cool. And now we can dig into the next section just a little bit. So now we're talking about random variables and probability distribution. So a random variable is just a function that assigns a value to each event in a sample space, right? So I can assign some numerical value and get a function and then define probability that way. It says, despite its name, a random variable is not random or a variable, which is really confusing. And a lot of things in statistics are named really confusingly. But it's a function with a numerical value defined on the sample space. For example, here, my random variable on a sample space of flipping 3 coins could be, for instance, the function that tells me how many heads I flipped. So for the first option of tails, 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 I flip 0 heads, and so on and so forth. For the probability of the occurrence of either 0 head, 1 head, 2 heads, or 3 heads in a simple 3-coin toss, we can write it as the probability of x, where x represents 0, 1, 2, or 3 heads. And it says that the function p is called the probability distribution of a random variable. Right. One common thing that's seen in statistics sometime, I'll grab out a piece of paper, is the distribution of probabilities spread out over something. A common probability distribution is called the normal curve. This is also known as the bell curve. It says that given a set of data, stuff tends to average towards the middle and then spread out evenly like this. This is represented e to the minus x squared over 2. It's the function used for that. It's a very significant thing. If you do behavioral analysis or any sort of statistic stuff, more than likely you'll see something like this. Cool. Here it says to find maybe probability that 2 heads are getting flipped out of 3 coins, we find the event where exactly 2 heads occur. So these events are 2 heads flipped second and third, a head first and a head third, or a head first and a head second, right? This was basically problem 2 on the quiz on Monday, right? I told y'all to write up the sample space, and then I asked y'all specifically to find where 2 tails were flipped. Cool, cool. It says, thus, the probability of flipping 2 heads is the number, let me zoom in a little bit. Number E, this is my event happening, over the number of events in the space total. Now it says to solve for these different things. So the probability of flipping 0, well, we look here, only one of these has 0. So 1 over the total was 8. The probability of flipping 1, there's 3 ways that happens. 3 over 8. And the probability of flipping 3, there's only one way that happens. 1 over 8. If I add all these together, I get 1. So 3/8 plus 1/8 plus 3/8 plus 1/8, all of those adds together to 1, which makes sense. Again, the probability is always adding up to 100% everywhere. It says here that the probability distribution of a random variable x, denoted at p of x, satisfies these things. So they're all going to be fractions. Oh, come on. I had to sneeze so bad and it went away. Oh, that's so embarrassing. Cool. The probability is going to be a fraction between 0 and 1. It could be equal to 0 or it could be equal to 1. And x is listed out in this amount of probabilities. The sum of all of the probabilities is 1, where the x1, x2, xn, yada, yada, are the range of values of x, right? Range of values here, and I add them all up. Probability of 0 plus probability 1 plus probability of 2 plus probability of 3, and that gives me 100% there. The expected value is what you expect to happen. A common example of this is, say I'm flipping a coin 100 times, the expected number of heads that I flip is 50, right? It should be a 50-50 split. You should get an even number of heads and tails. What actually happens is that that's not true. You're more likely to flip a tails than a heads, especially with a quarter, because the head is just a little heavier than the tails. So this is just saying what is expected to be the result after you run the experiment for an extended period of time. So suppose that the experiment of tossing 3 coins was repeated many times, what would be the average number of heads per toss, or tails for toss, whatever. And so the probability distribution, given these, we expect the value to be this. So in the long run, we would expect the average number of heads per toss of 3 coins to be 1.5, which makes sense, right? We expect the toss to have exactly, like on average, the same amount of heads as tails. It doesn't make sense that in one toss, a coin is half heads and tails, but over time, it averages out. And we can do this. We denote this E of X. This is the expectation value. And we just multiply all of our probabilities by the random variable that we were assigned to it, right? So the number of 0 heads plus the number of 1 heads times its probability plus the number of 2 heads times its probability, 3 heads times its probability gives us our total value. Cool. It says note the expected value is not a value that will occur in a single experiment, right? I can't get 1.5 heads flipped on one turn, but averaging out several turns, that's what it will come out to. So it says to compute the expected value of a random variable, we're given the probability distribution. So here, maybe x1 was 0, x2 was 2 or 1, so on and so forth. And then we denote this as EX, expectation value of x, is the first variable times the probability of it, plus second variable times probability, which is exactly what we saw up here. It says the steps to computing expected value of a random variable are first, form the probability distribution, and then multiply each probability by its variable assignment. For example here, if the probability distribution for a random variable was given in this, what is the expected value of x? And always check that the probability row sums to 1. This here does sum to 1. 0.2 plus 0.6 plus 0.2 is 1. And now I just multiply this out. 0.2 times -5 plus 0.6 times 0 plus 0.2 times 3. It's -1. So negative 0.4 right there. There's a point there. So the probability, the expected value is negative 0.4. Not sure what this experiment is. Maybe it's like what the expected value of a car's depreciation is over time or something like that, where maybe this is the years or something. I don't know. But this is a pretty straightforward thing. We just multiply the probability by the assigned random variable. Example 2 says you draw and keep a single bill from a hat that contains 1, 10, 20, 50, and 100. What is the expected value this is going to give you? Right. So I can set up my probability table here. 1, 10, 20, 50, and 100. This is my xi and this is my pi. So this is just my value here is just my random variable is just the value of the bill. All of these I have an even chance of, oh, it says you draw and keep. Each of these I have an even chance of doing though. Like if I draw it and then I repeat the experiment, maybe I go to a different hat that has all those bills in it, I draw it and so on and so forth. Each of these I have an equally likely chance of drawing. So these are all 0.2. And then my expected value is going to be, I just multiply the probability by each of these. So 0.2 times 1 plus 0.2 times 10 plus 0.2 times 20 plus 0.2 times 50 plus 0.2 times 100. And looking at my calculator, 0.2 times 1 plus 10 plus 20 plus 50 plus 100. How about the 400? 100. And I get $36.2. So if I continue this out, the average draw is going to be between the 20 and the 50. I'm significantly more likely to draw somewhere in that range. If I did this for, 100 numbers, the average out would be something different. But for this example, 36.2 is the average. And interestingly enough, that's just the average of these right here, right? The average of these values. Since everything has equal chances of happening, the expected value is the average of the elements here, the random variables. I think, honestly, I'm going to stop here so that on Friday we can finish up this chapter and then I can answer any questions about the test. So if you have questions about anything, of course, email or text me. I'm going to open up the homework for 8.5 so that you can get working on that. And yeah, if you have to make up a quiz or anything, also text or email me to set up a time for that. Usually that's going to be during the math center that I sit or during my office hours. If you don't have anything for me, oh, what's up? I could probably find a practice test to send out to y'all. So send me a text or an email to remind me of that, and I'll do that for you. Good question.
Are you gonna
Yes. I recorded Mondays. I just haven't uploaded it to YouTube yet, but I've been recording all of these.